Good morning or good afternoon, professors. We are B-97 and we are here to make a presentation on our minor project winter semester 2022 to 23 file encryption using Fibonacci series. This is the agenda for our project. Here we have abstract, objective, introduction, literature review, design and methodologies, standards and policies, implementation, testing, input-output, demo, conclusion, feature enhancement, web references, plagiarism report, and poster presentation. Abstract. So in our daily, in modern day, in our daily lives, we are using the internet. The internet uses unguided transmission medium, which means it is using radio wave, infrared wave, and microwaves to transmit and send information. Unlike guided medium, which uses wires and it can only transmit in a predictable direction of the wire, given physical security, it will not be tapped by others. However, in case of wireless guided medium, the transmission tower will transmit our information in 360 degrees everywhere, which can easily be tapped by anyone who is not the receiver. Since we do not want this, we need to carry out encryption, so only the receiver who has the key and the proper de-encrypting technique can read out message. Our project Fibonacci sequences to encryption, it falls under cyber security and cryptography domain. We are using plain encryption technique here, and we are also expanding it to create 8x8 matrix table instead of the classical 5x5. The aim of this project is to use a program to generate Fibonacci sequences, has the Fibonacci sequences, then use it to generate the preferred matrix table and use it for encryption and decryption. The scope of this project is to be able to ensure that our ciphertext is accurate, and then when decrypting the ciphertext, you will get the upper plain text without any iteration or changes. The information that we receive must be, after encrypting and decrypting, must be exactly the same as the information that we have inputted. The second scope is able to choose the amount of length of Fibonacci sequences as well as the starting point. Introduction. The Fibonacci process using is simple. We are basically adding the previous numbers. The first two numbers in the sequence will always be 0 and 1. Adding 0 and 1, the third sequence is 1, 0, 1, 1. Adding 1 and 1, the fourth sequence is 2. Adding 1 and 2 and 1, the fifth sequence is 3. Adding 3 and 2, the sixth sequence is 5. Adding 5 and 3, the seventh sequence is 8. Adding 5 and 8, the ninth sequence is 13, and so on. We decided to choose Fibonacci sequences because in order to have a good thing, we need to ensure randomness, unpredictability, and low collision. We decided to so for this purpose we have selected Fibonacci sequences. Also, Fibonacci sequences are exponential in nature, but they are not exactly exponential as doubling of the values, but rather they will increase in somewhat an exponential manner, but it is difficult to predict as it's not linear. Suppose we are expanding 2 by the power of 2, then expanding it again and again, it will become very predictable. But in case of Fibonacci sequences, since the value is not doubling, it is only slightly, it is increasing massively, but it is not increasing to the exact double. Thus, by using brute forcing, malicious recipients or hackers will not be able to brute force and break our algorithm. In literature review, here we have done the literature review for several papers. In total, we have 10 papers in our references which we have reviewed. Here we can see it is in the correct format: author name, paper title, the paper publisher, and the time the paper has been published, and then the description of the paper. So here, in the first case, generation of rectangular matrix key for ill cipher algorithm using paper cipher. We have explained that in here this technique expands 5x5 matrix into 10x9 matrix. It has 6 iteration steps to create a more complex encryption process, and once it is encrypted, it can be decrypted using the same 10x9 matrix. It's more complex, but it also ensures security. Thus, similarly, we have 9 more papers which we have reviewed in short. Moving on to the next agenda: design and methodologies. We have 3 modules here. One is encryption module, second is decryption, and then the third module is Fibonacci sequence generation and hashing. So for the encryption, once we get the secret key from the Fibonacci sequences being hashed, the key is used to create the paper matrix table, and then this paper matrix table will be used to transform the plain text into a ciphertext. In order to do that, the plain text message is split into digraphs, which means it is split into 2 different characters which are assigned to it. For this purpose, it is important for these digraphs to not contain the same character. If the digraph contains the same character, we will use a pure word such as X. And also, if we are within the last character, but if it is a singular character rather than being able to create a digraph, we will have to again use the filler word, which is the filler alphabet, which is the X. So, a description of how our encryption process works: we first create the matrix grid, and then in there, the first characters will be the characters which is contained in our key. Then once the key is depleted, we will fill the remaining portion of the matrix in a sequential manner. Once that is completed, we will read the latest of the digraph and see the position on the matrix. It will be shown on the diagram on the next slide. So here, the digraph is, in the first case, the digraph is I and H. It is plain text. By looking at their position, if since they are in different row and different column, I has to be shifted to the position of the column position of H. So I becomes M. H has to be shifted to the column position of I. So H becomes A. In second case, they are in same column, so they will be shifted downwards by 1 position. So E and D. E becomes D, D becomes O. In third case, H and T is the digraph, and they are in different row and different columns. So H is shifted to B, T is shifted to Z. Likewise, in N O digraph, they are in different column and different row. L is shifted to A, and O is shifted to N. So thus, here as explained in our encryption steps, depending on the position of the characters inside the digraph on the matrix, we are either shifting it to the right if they are in the same row, we are shifting it to the bottom if they are in the same column, or we are shifting to their column locations if they are in different row and different column, as explained in the bottom 2 points. Model 2 is encryption. In this model, the steps are exactly the same, the reverse of the encryption steps, and also we are creating the key using the key which has been generated to create the table in the same manner. So this is decryption diagram. The steps are similar as previous one. M has become I, B has become H, the diagram DO, D has become E, O has become D, and then in third case, A has become H, Z has become T, and then in fourth case, A has become L, and N has become O. The third mode is Fibonacci sequence generator. Here, I have posted a diagram of the flowchart for Fibonacci sequence generation. First, we read N. N is the total number of sequences to be generated for Fibonacci sequence. If N is greater than 2, then we will generate 2 sequences. The starting numbers in the Fibonacci sequence is 0 and 1. Thus, A is 0 and B is 1. Then we will run it under the following steps: T equal to A plus B, A equal to B, B equal to T. This will generate the next upcoming Fibonacci sequences until the total count is equal to N. And then hashing will be carried out. In case of hashing, here the outputted Fibonacci sequence will be reversed. Suppose we are getting 13, it will be reversed to create 31. Then it will be done modular division. So by doing modular division, the 31 is still 31 because it is less than 64. And we are getting the output which is used as key for creating the matrix table for paper matrix. Suppose the Fibonacci sequence output is 35. Reversing it will become 53. Then doing modular division by 64, the key is 53. But suppose by reversing we are able to get 65. Then doing modular division, the key will become 1, not 65 because it is greater than 64. Moving on, standards and policies. For our project we use mainly two applications. One is Python compiler, which is Google Colab Jupyter. This Google Collaboratory is a product from Google research team that allows anyone to write and execute Python code through the web browser. We use this because we are collaborating online with each other. So it was easier to use online compiler rather than offline compiler because Google Colab can be shared through Google Drive to our team members. We are also using GitHub because it allows us to collaborate easier by storing program code online and to validate changes made in the program code. For both of them, they are using the international security standard, which is ISO IEC 27001. For implementation, we have created various diagrams: architecture, data flow, use case, class, activity, sequence, and collaboration. Here in the architecture diagram, I have separated the program into various components depending on how they are executed in the software space. First module contains Fibonacci sequence generator. This will generate the Fibonacci sequence, and then The Fibonacci sequence is hashed in the module 2 to create our key. This key is sent to the third module, which will be used to create 8x8 matrix for our encryption process. Encryption matrix contains A to Z, Z to 1, and special characters starting from exclamation mark till all those special characters on the keyboard. First, keys will be imported into the matrix, then the encryption matrix contents which have not been inputted through the keys will then be inputted sequentially into the matrix until the 8x8 matrix is completely filled. Then in the main component, the plain text or the input is either encrypted or decrypted using the matrix. So by encrypting, we are getting ciphertext from plain text as can be seen here. In data flow diagram, we have specified the flow of data. Mainly, there are two flows from the user, which is the origin point. The first flows go into Fibonacci number confirmation. So since I wanted to emphasize and key randomness, we are able to start from any point of the Fibonacci sequence, whether 13 or 21 or 157, not just 0 or 1. Thus, first we will input a Fibonacci number. It will be confirmed. Once it is confirmed, then we can move on to the Fibonacci sequence generation. The total number of sequences we have to generate, it will generate, and then it will be passed on to the hash generator. Hash generator will reverse the numbers and then carry out modular division 64. Then it will result in keys, which is usual creation of paper matrix table. The second data flow part from the user is the input. The input with the plain text. It is encrypted using the paper matrix table, resulting in ciphertext, which will be stored in storage component. Since we need to carry out encryption as well as decryption, we can take out the ciphertext from the storage, and then using the paper matrix table, we can do decryption process, then get the plain text, which will again be stored in the storage. The storage has input and output part, outgoing and incoming part to both ciphertext and plain text components. Use case diagram. Here, the only actor is the user. Thus, in this diagram, we only have the users, and in the actions, we have running the program, chosen to encrypt, inputting file or string, and then carrying out the encryption process, choosing to decrypt, inputting the encryption string, etc. The output work will be stored, and then we can see the output on the monitor. In class, we have mainly 4 classes. The first most starting class is Fibonacci sequence. Here, we generate the number of sequences using the generate method. N integer contains the starting number of the sequence, and then the sequences integer list contains the output of the generate method. We will pass the sequence list to the hash class. The hash class uses the sequence list and the hashing method to get the key list output. The key list is passed onto the encryption class or the decryption class depending on which one we are trying to carry out. The encryption class contains plain text from the user. Using the key list, the encryption matrix is generated using encrypt method, and then the plain text is converted to ciphertext using the encrypted algorithm. Similar for decryption, we have the ciphertext, which is either taken from the user or taken out of storage. Then using the key, we create a matrix, and then using decrypt method, we are able to convert it into plain text. Here, the total activity of the program has been displayed in simplified format. So we have Fibonacci sequence, which is the first step, Fibonacci sequence generation. It is hash, which is the second step, being either encryption or decryption from the user. So for encryption, we will have to import plain text. For decryption, we will have to import ciphertext. Then after carrying out the proper encryption or decryption, the output will be stored. This will result in the termination of the program. Thus, this is the total activities carried out by the program. Sequence diagram. There we have the sequence of the actions which the program will carry out. Some encryption, the analysis of string, the input of file, the processing of input and decryption process. First, the encryption string is carried out, then input, file, and decryption. The actions have been laid out in sequential manner. In collaboration diagram, all the components of the program has a collaboration which can be seen. The actor user helps in the generation of Fibonacci message, which is hash, resulting in keys, which is sent to the encryption and decryption component. With the keys, they are able to convert plain text into ciphertext and ciphertext into plain text, which is finally stored in the storage component. In unit testing, we had mainly 3 programs. First program was Fibonacci sequence Python program, second was hashing Python program, and third was encryption Python program. By using them individually without any integration, we were able to get the correct output. Thus, our unit testing was successful. For functional testing, we were able to test the function. They gave us the they carried out the function properly. Fibonacci sequences program outputted the Fibonacci sequences. Hashing program outputted the hashing output after converting the number and doing modular division 64. And the encryption program was able to successfully generate the Napier matrix 8x8 matrix table. In black box testing, we only looked at the input and output. We were able to get the correct output, expected output from the input. So we put a check on the black box testing. In white box testing, we used the Python compiler to see if our program had any syntax error or any other errors, whether grammatical or logical error. We were able to verify that our program did not contain any syntax error. And we executed the program. It gave the proper output from the input. So we declared that we passed the white box testing. So here, this is our input and output. The program is asking for plain text message. The key has already been generated. So the plain text message is Ashtaparangi. Here Ashtaparangi, and using the encryption and decryption process, this is the ciphertext, and by decrypting we are able to get Ashtaparangi again. This is a video. Actually, this is not a video but a screenshot, but our video is on Google Drive, which we will explain in the final details. And here in conclusion, we were able to expand the Napier matrix into 8x8 to contain numbers, special characters, and special symbols and spacebar. It is important for us to be able to contain special symbols and characters as well as numbers, because in World War II, Napier matrix was broken by the Germans using word association technique. Word association means that they were able to predict the output using a dictionary. So, since our ciphertext does not only contain alphabet but also special characters and numbers in ciphertext, the brute forcing technique of using word association cannot be carried out. This ensures in the security of our method. Likewise, using Fibonacci sequences, we are able to promise randomness, no collision, and exponential capability. This allows our technique to be um, less resource intensive and quicker than DSA, RSA, and SHA 512 algorithms. And another important thing is that the internet is a complex infrastructure. It is ever expanding, but it is also ever decaying. Every day, thousands of computer servers and nodes are being damaged due to either lack of maintenance or high workload. There are people who maintain and restore these nodes, but they are not sufficient on a worldwide scale. Therefore, in order to improve the redundancy by introducing by uh, allowing this technique to be used on legacy computers, as well as reducing the hardware strain on older systems as well as current systems, we are able to improve the lifespan of the various nodes and servers on the computer. Internet infrastructure, future enhancement. For future enhancement, uh, for future enhancement, we will carry out studies and experiments to compare our method with RSA and SHA techniques. Currently, we are using the claims made in other scientific scholar papers, which says that our expanded table technique is as secure as RSA, DSA, and SHA. However, if we are able to carry out our own study, we can express our claim with a standard credibility and validity. Another important point is that um, we are using the program to convert ACRI symbols. However, the internet uses Unicode, so in the future we have to expand our program to include Unicode and convert Unicode into plain text and ciphertext. The web references link in this Google Drive, we have uploaded our uh, references paper which we use for the implementation of this project. In references, we have all the references which we have cited and studied. We have in total 10 references. This is the plagiarism report of our PPT. As you can see here, we were able to get 17% similarity index. This is our poster presentation. We will present it in our final review in a paper. Thank you. This is the end of our presentation.